Okay, we're gonna continue with uh, our study of in Physics 1305 with the chapter 2 in conceptual physics, the Newton's first law of motion, inertia. So we're going to these are some of the ideas that we're going to cover in this lecture. Aristotle's idea of motion, Galileo's concept of inertia, Newton's first law of motion, net force and vectors, the equilibrium rule, support force, equilibrium of moving things, and the moving earth. So those are some of the topics that we'll cover. Aristotle is he had certain ideas. A lot of his ideas got passed on, Aristotelian ideas, and these were he talked about natural motion. Every object in the universe has a proper place determined by a combination of the four elements that were known at the time: earth, water, air, and fire. Any object not in its proper place will strive to get there. Example: stones fall, puffs of smoke rise. That was their nature to, and stones that roll will come to a stop. Things that fall, they'll roll, but they'll eventually want to come to a stop. That was his idea of natural motion. Straight up or straight down for all things on Earth. Beyond Earth, motion is circular. For example, the sun and the moon continually circle the Earth. In their eyes, the sun circled the Earth. They had a geocentric model of the solar system, that even the sun circled the Earth. It wasn't until Copernicus that we realized that it's a heliocentric, that everything revolves around the sun. And he had there was natural motion and there was violent motion produced by external pushes or pulls on objects. An example would be the wind imposes motion on a ship through the sails. So that was his differentiation between natural motion and violent motion. Okay, and then Galileo kind of put those ideas behind him in the 1500s. Galileo discovered that objects of different weight fall to the ground at the same rate in the absence of air resistance. Aristotle thought heavier things fall at a faster rate than lighter things. And we'll see, when you take into consideration air resistance, yes, if you drop a 1 kilogram weight and a 2 kilogram weight, they're going to fall at the same rate. But if you drop a 1 kilogram weight and a feather, they're going to, because the feather has more air resistance, they're going to fall at different rates. I even have a little demonstration of that where we use coffee filters. A single coffee filter will drop at one rate, and 2 coffee filters will drop a little bit faster. Why? Because there's more air resistance. And I'll also send you a link of a video where a bowling ball and feathers are dropped in a high vacuum, and you'll see that they drop at the same rate. It's only because of the air resistance that the feathers drop slower. I'll put that link in the in Canvas and along with the lecture notes. Okay. And Galileo also said that the story of him dropping 2 cannonballs off the side of the Leaning Tower of Pisa, that I think most people think it's apocryphal. It's not really a real story. It may be, but it makes for a nice story. He also proposed that a moving object needs no force to keep it moving in the absence of friction. So to Galileo, force is a push or a pull. And inertia is a property of matter to resist changes in motion. And it depends on the amount of matter in an object, its mass. Let me give you a little example. Let's say you go to the grocery store, you park close to the front of the grocery store. And when you come out of the grocery store, there's a shopping basket, an empty shopping basket, parked behind your, or sitting behind your car. And do you run to the management and complain, hey, there's a shopping basket blocking my way? No, you don't run to the management. You just push the empty cart out of the way. It's very light. But let's say you come out of the store and some delivery guy, let's say a bread truck, he thought, well, this won't take long. I'll just park here and run in and deliver my stuff. Do you just, like you did the shopping basket, move the bread truck out of the way? No. Why? Because it has more inertia. It has more mass. The shopping cart has little mass relative to the bread truck, so you can move it easily. The bread truck has a lot of mass, a lot of inertia. You can't move it out of the way. So let's take a similar situation. Let's say you have a brand new car, whatever you want to call it, brand new Corvette or brand new BMW, whatever your favorite car is, and you don't want to get dinged, so you park it far from the entrance so that nobody will open their door next to you. But it happens to be on a slight incline. And as you get out of the car, you see this runaway shopping cart coming towards you. Do you panic? No. You just kind of step in front of the cart, slow it down, stop it, so it doesn't hit your car. But you get out of your car and you see a runaway bread delivery truck with no driver. Apparently, he forgot to put on his parking brakes. Just had to ride for your car. Do you get in front of it and stop it? No. You're gonna get out of the way. Why? Because the truck has a lot more inertia. You can't stop it. It has much more mass. So inertia is a property of matter to resist changes in motion. The bread truck is going to have a lot more resistance to its change in motion than a shopping cart. And it depends on the amount of matter in an object, the mass, the amount of mass. A bread truck is much more massive than a shopping cart. Okay. Galileo's concept of inertia, he noticed that balls rolling down sloping planes picked up speed. The slope downward, the downward speed increased. And he also noticed that upward sloping planes, balls rolling upward planes, they slow down. So a ball on a horizontal plane maintains its speed indefinitely. That's in the absence of any friction. If the ball comes to rest, it is not due to its nature, but due to friction. Aristotle said, well, it's its nature to stop, but Galileo realized that it's only the force of friction that causes it to slow down. If you've ever played with an air hockey table, if you take the air hockey puck and give it a slight nudge, you'll see that it slides for a long period of time without slowing down. The air makes it float and it gives it an almost frictionless surface. Okay. Let's see. Let's take a little quiz. The use of inclined planes for Galileo's experiments helped him to eliminate the acceleration of free fall, discover the concept of energy, discover the property called inertia, or discover the concept of momentum. And it's C, discover the property called inertia. Note that the inertia is a property of matter, not a reason for the behavior of the matter. Okay. Newton's first law of motion. Every object continues in a state of rest or at uniform speed in a straight line unless acted on by a non-zero net force. So a lot of people say objects at rest stay at rest. Objects in motion tend to stay in motion. But you have to add that caveat, unless acted upon by an external force. So the force of friction is what causes a ball rolling on a grass field causes it to stop. That's Newton's first law of motion. Every object continues in a state of rest or at uniform speed in a straight line unless acted on by a non-zero net force. Okay, vector quantity. A vector is a quantity whose description requires both magnitude, how much, and direction, which way. And it can be represented by arrows drawn to scale called vectors. The length of the arrow represents the magnitude, and arrowhead shows the direction. Example, force, velocity, acceleration. Let me just, let's do a new share, and I'm going to switch to my iPad, and I've got a vector drawn. Let's see, it's not there yet. There it is. There's a vector. It's got a magnitude, you know, how long it is. This is how long it is. And it's got a direction. Now, this is just information. It's not, let's take this vector and let's, oops, that's the last one I did. Let's erase this. And let's do that again. And let's copy that. And now, if I paste it and paste it again, those all three of those are the same vector, because a vector is just a representation. Even though they're in different starting locations, they are all the same vector. It's just a concept. It's just a vector is just a concept, and you can, you know, I live in the medical center, and when I drive to St. Philip's, I'm driving generally in a east-southeast direction to get to St. Philip's. But at times, I mean, at times I'm going east, at times I'm going south, at times I'm even going north, you know, depending on how the highway goes. So at each one of those moments, I have a different direction, but my general direction would be east, southeast. Now, so when a vector, to change a vector, you either need to change its direction or you need to change its magnitude. Those are the two things that make up a vector: a magnitude and a direction. So if you change either one of those, you have changed the vector. Change the direction. So if I, you know, let's try to duplicate this, but let's get it coming down this way. That is not the same vector. That's going in a downward direction. So that's this vector and this vector are not the same thing. Okay, let's go back to the PowerPoint. Okay, click on that. Okay, so a vector can be represented by arrows drawn to scale called, a force can be represented by arrows drawn to scale called vectors. The length of the arrow represents the magnitude, and arrowhead shows the direction. So force, velocity, acceleration, all of these are vectors. Okay. A net force is a combination of all forces that act on an object. Example, 2 5-Newton pulls, force is expressed in newtons. 2 5-Newton pulls in the same direction produce a 10-Newton pull, a net force of 10 newtons. If the pair of end pulls are in the opposite direction, the net force is 0. So here we have the first one. I think you can see my cursor. 5 newtons plus 5 newtons is 10 newtons. And here we have 5 newtons in this direction, 5 newtons in this direction. Well, those net force, the sum of those two, since one is positive and one is negative, the sum is 0. Okay, a cart is pulled to the right with a force of 15 newtons while being pulled to the left with a force of 20 newtons. The net force on the cart is 5 newtons to the left, 5 newtons to the right, 5 newtons to the left, 25 newtons to the left, or 25 newtons to the right. Well, it's not going to be the 25 or the 25. The difference is going to have to be 5. And it's since the pull to the left is greater, it's 5 newtons to the left. The two forces are in opposite directions, so they subtract. The direction is determined by the direction of the larger force. Okay, what is the net force acting on the box? We have 5 newtons in this direction, 10 newtons in this direction. So what do you think it's going to be? It's not going to be 15 because they're in opposite directions. So it's going to be 5 newtons. The difference between them is 5 newtons. But what's the direction? Well, this is the greater one. So it's going to be 5 newtons to the right. There it is, 5 newtons to the right. Okay. Now, vectors. Again, a vector has magnitude and direction, is represented by an arrow. And as we said, the examples are things like velocity, force, and acceleration. A scalar quantity has only magnitude, but not direction. Examples, mass, volume, and speed. Mass is, something weighs 1 kilogram or 2 kilograms. There's no direction to it. The force of gravity pulls it down towards the Earth, but just the mass itself is just 1 kilogram. 1 kilogram on the Earth is 1 kilogram on the moon. They both have the same amount of mass. Now their weight is different because the acceleration due to gravity is different on the Earth than it is on the moon, but their mass stays the same, but its mass stays the same. Volume, 10 cc's is just 10 cc's. What is the direction of 10 cc's? Well, that's a nonsensical question. It doesn't, you just have 10 cc's. The speed, you can be going 50 miles an hour. Now, if you say you're going 50 miles an hour due north, you've just turned that speed into a velocity. A velocity is a vector with both magnitude and speed and magnitude. Okay, but speed by itself is just a scalar. Resultant, the sum of 2 or more vectors. For vectors in the same direction, they add arithmetically. For vectors in opposite directions, they subtract arithmetically. 2 vectors that don't act in the same or opposite direction, you have to use the parallelogram rule. And I'm going to have a little assignment, a fun little assignment. We're going to be using Walter Fent little applications that I think they'll be helpful. So 2 vectors at right angles to each other, that's easy. You just use the Pythagorean theorem. So let's go over here very quickly and go back to my iPad. I'll get a new sheet. And here we go. Let's say I have this vector here. And let's say I have this vector here. Now, how do I add those? What I want to do is I want to copy that, and I want to paste it over here. And let me copy make sure I get just that. Paste. That's roughly what I want. And now I'm going to change colors so that you can see the resultant. So the resultant would be a vector right there. That blue one is the resultant vector of this vector plus this vector. That's what they mean by the parallelogram method. Again, if it's just a right angles, if we have one, it's okay that I'm using red. If we have just like this, then we use the resultant. That's the resultant where this is, let's say, the x and this is y. The resultant is equal to the square root of x squared plus y squared. That's easy if you have a right angle. Okay, let's go back to the PowerPoint and get through this. Okay. Referring to the, when I did the previous one, the resultant was the diagonal line, the bottom one I called the x component. So it was a component of the resultant vector, and the vertical, the y, it was a component. Now, given that information, let's look at these. Referring to the figure, which of the following are true statements? 50 newtons is the resultant of the 30 and the 40 Newton vectors. Okay, here's the 30, here's the 40, and sure enough, the 50 is a resultant. So that one's true. The 30 Newton vector can be considered a component of the 50 Newton. Well, that's the y one. Yes, it is a component of this one. The 40 Newton vector can be considered a component of the 50 Newton. There's the 40. It is a component of the 50. So the answer is D. All of the above are correct. Okay, and let's see. Nellie Newton hangs from a rope as shown. Which side has the greater tension? Now there are three forces acting on Nellie. Her weight, mg, that's mass times the gravitational acceleration. G is the gravitational acceleration. Why they introduced this so early without explaining it, I don't know, but I'm explaining it to you. mg is her weight. M is her mass. G is her is not only hers, everybody's gravitational acceleration, which is 9.8 meters per second squared. You can use 10 meters per second squared as a general rule, and you won't be off by much. Her weight is mg. The tension in the left side of the rope is one of the forces, and the tension on the right side of the rope is another force. Okay, so because of the different angles, different rope tensions will occur on each side. Nellie hangs in equilibrium, so her weight is supported by two rope tensions, adding vectorially to be equal and opposite to her weight. We use the parallelogram rule, and it shows that the tension in the right hand is greater than the tension in the left hand side of the rope. You can see that this one, this green here, that's this right hand tension, and this one here, that's this left hand tension. So these, you can see that green, that's translated over here, and there it is over there. They're using the parallelogram method to get these two vectors and get the resultant vector. This vector here should be exactly the downward force. If one was greater, she'd be moving, and she's not moving. Okay. A string holding up a bag of flour. Two forces act on the bag of flour. The tension force in the string acts upward. The force due to gravity acts downward. Both are equal in magnitude and opposite in direction. When added, they cancel to zero. So the bag of flour remains at rest. If they didn't cancel to zero, that meant there was a net force and there would be motion. Whenever you don't have motion, you have a net force that equals zero. Okay. Now this little sigma, capital sigma, is the letter we use for sum. So the vector sum of forces acting on a non-accelerating object equals zero. Non-accelerating can mean two things. It can mean it's still, or it means it's going at a constant velocity. Okay, constant velocity. The vector sum of forces acting on a non-accelerating object equals zero. So in equation form, the sigma F, the sum of all forces, equals zero. The red arrows represent force vectors. The sum of the two upward force vectors minus the sum of the three bottom force vectors equals 0. We say the forces cancel to 0 and the system of Burl, Paul, and the staging is in equilibrium. In other words, the tension in the ropes holding Burl, Paul, and the staging is equal to their combined weight. Okay. The equilibrium rule, the sum of the forces equals 0 applies to vector quantities, scalar quantities, both of the above or none of the above. I'm going to say vector quantities because the forces have direction. They have directions upward, downward, or as we'll see, to the side. We saw it already with the vectors that on the blocks where one was going one way and one was going the other. The equilibrium rule applies to the forces acting on an object in steady motion. Forces are vectors and the directions of the forces are accounted for in the vector sum. Okay, a support force, also called the normal force. The normal means perpendicular. So if you have an object like here, the normal force supporting it would be at a perpendicular to the surface. So normal means perpendicular. The support force, the normal force, is an upward force on an object that is opposite to the force of gravity. Example, a book on a table compresses atoms in the table, and the compressed atoms produce a support force. So the atoms from the table holding my laptop in front of me apply a force equal to the force of the downward pull of the computer to let it rest. If they weren't equal, there would be motion. If the sum of the forces is not equal to 0, then there's going to be motion. Okay. When you understanding the support force, when you push down on the spring pushes back up on you. Similarly, when a book pushes down on the table pushes back up on the book. We'll see that when we get to another Newton's law. Summarizes for every action there was an equal and opposite reaction. Okay. When you stand on two bathroom scales with 1 foot on each scale and with your weight evenly distributed, each scale will read your weight, half your weight, 0, or more than your weight. Now let's think about this. If they each, let's just say you weigh whatever you, let's just say 100 pounds. If the left one's read 100 and the right one read 100, that would be 200 pounds. That's not going to be. It's going to split it in half. It's going to be half your weight. Half your weight. You are at rest, so the sum of the forces equals 0. Forces from both scales add to cancel your weight. The force from each scale is 1/2 of your weight. Okay. Let's see. Equilibrium, a state of no change with no net force acting. So there's static equilibrium. As an example, a hockey puck at rest on slippery ice. Dynamic equilibrium. Example, the hockey puck sliding at constant speed on a slippery ice, or like I said on the air hockey table, the puck just sliding on the cushion of air. It's in constant motion. Both of those are in equilibrium. So equilibrium does not necessarily mean still. It can be still, it can be standing, stationary, or it can be moving at a constant velocity. If it's not a constant velocity, then there's acceleration somewhere. So equilibrium means constant velocity. Okay. Equilibrium test, whether something undergoes a change in motion. A crate at rest is in static equilibrium. There's no change in motion. It's just sitting there. Example, when pushed at a steady speed, it is in dynamic equilibrium, no change in motion. Your push is exactly equaling the amount of friction that would keep it still, and it's It's sliding in at a constant velocity. Okay. A bowling ball is in equilibrium when it is at rest. It moves steadily in a straight line path, and both of the above are true, or none of the above are true. Think about it for a bit. From what we said, they're both true. Both of the above. Equilibrium means no change in motion. So there are two options. If it's at rest, it continues at rest. If it's in motion, it continues at a steady state, at a steady rate in a straight line. Okay. You push a crate at a steady speed in a straight line. If the friction force is 75 newtons, how much force must you apply? Remember, for steady state, for equilibrium, the sum of the forces must be equal. So if the friction is 75 newtons, then the applied force has to be 75 newtons. So C is equal to 75. C. The crate is in the dynamic equilibrium, so the sum of the forces has to equal 0. Your applied force balances the force of friction. Okay, now the moving Earth. Copernicus proposed that Earth was moving in a circular motion around the sun. The idea was refuted to people. They said, if the Earth moved, how could a bird swoop from a branch to catch a worm? In other words, they thought, okay, if the Earth is moving, if the bird were to go down and the Earth were moving, then he would go at a diagonal and not straight down. The solution is that as it swoops due to inertia, it continues to move sideways at the speed of Earth along with the tree, worm, etc. In other words, as the Earth is circulating, it's already got an initial speed from the rotation of the Earth. Well, that as it swoops down, it moves with that initial speed. Okay, here's you are riding in a vehicle at a steady speed and toss a coin straight upward. Where will the coin land? Now the key here is steady speed. Really, it should say steady velocity, because a change in direction would be a change in velocity. So if you were throwing this coin up and suddenly the driver turns, your coin is going to shoot off in one direction or the other. So I would rather he use a steady velocity. So you're riding in a vehicle at a steady speed. I'm going to say steady velocity and toss a coin straight upward. Where will the coin land? Behind you, ahead of you, in your hand. It's going to land in your hand because that coin has the same velocity as you in the vehicle. Due to the coin's inertia, it continues sideways with the same speed as the vehicle in its up and down motion, which is why it lands in your hand. Now, what about when you threw it up, if the automobile suddenly stopped, it would move forward. Or if you threw it up and let's say you're at a stoplight and you threw it up, if the car suddenly took off, it might hit you in the forehead because it wants to stay in the motion that it was. Okay. And that's the end of the lecture. I'm going to add links to a couple of videos. One is a space station video showing inertia. One is the feather and the ball, I think it's a bowling ball, in a vacuum chamber that they fall at the same rate. And I'm going to send a little app, the Walter Fent app. It's a fun little app to play with that helps you see vectors. Okay, but that ends chapter 2, and we'll end the video at this point. Thank you.